Hi, good morning, everyone. Can you hear me?
Yes, Prof.
All right. Loud and clear?
Yes, that's Prof.
Okay. So, I'm sharing something. Okay. Okay. Can you see my slides?
Yes,
Alright.
Prof.
Okay, so I already discussed with you last week regarding on the non-parametric analysis. We are using a graphic approach instead of mathematics transfer functions. So now we are going to the transient analysis, okay, which can be we use step or impulse signals, okay, as the cause or the input of the system, standard input, and then we observe the output. So the model consists of a recorded output, okay, can be recorded, can be captured, okay, the graph or the data, okay, via USB or straight away to the hard disk. And this kind of approach is suitable for deriving crude models as what they call that as pre-testing, okay, pre-testing. Just to know the behavior, okay, is it first order, second order, third order, or higher order. So it will use some of the important time spec, which is time constant, time delays, and static gain, which is symbol as tau, okay, tau d, and k is the gain. And this one is very sensitive to the noise surround, okay. So it can be from handphone, it can be from 3-pin plug, okay. It can be from the aircon, okay. It can be from the lamp, okay, and so on. That will enter as a disturbance. So let's say we go for the step testing, which is using step signals, okay, analysis using a time response, okay. So we will look into the first order lag system with time delay and second order system with gain with time delay and a third order system. So for first order FUA'AD, first order identification from a step response using a methods of areas. So first we identify the gain plan, okay, using this formula. K equal to y infinity minus y0, the final value minus the initial value of the output and the input. And then we normalize the experimental data to obtain a unit step, okay. Then compute the error under the graph, okay, using the integral. Then compute the time, A0 over K, okay. And then compute the second area, which is A1, previously A0 or A0, as illustrated in the next figure, which is this figure, okay. So this is the time response first order with time delay. So this is the time delay. Okay, and this is the transient, and this is the final value. Okay, right. So the two remaining parameters of the proposed model in equation 6.1 are tau, the time delay, and the theta, where E is equal to exponent 1. Okay, so the constraint is the date time. Is it positive for causal plants, plant that have a higher disturbance? So the areas method for plant identification applied to a variety different plants with random disturbance. For example, we have several graphic figures of the time response. Okay, so you have the first graph here. Okay, which the real data is the plant. Okay, this is the real data. Real. And the estimated is the blue line. Okay, so if we get the estimated model, which is follow the real plant model, so this is considered very good. Okay, but sometimes due to the different or not accurate or not suitable model structure, so what we will get is something like this. The real one is by the red dot. Okay, real data, and then the estimated model cannot fit to the real plant data as shown in the number 2. Okay, but this one is considered need to be redo. Okay, by choosing a different model structure. And number 3 is considered as okay. Okay, because we inject the plant is the second order system. Okay, but the model actually like a step or square wave, which also not satisfied. Okay, the blue line cannot follow the real data as number 1. Okay, and then the number 4 is quite satisfied. Okay, the first estimation is follow the red dot data, but at this corner frequency, okay, as this corner, it fails to do so. So that's why we have to assume that the identification of the experimental black box using the method area sometimes have a disadvantage. Okay, you can see that from the 4 graph here. So only one graph is very good and satisfied. Okay, so noted that the identification strategy is reasonably robust to the noise and outlier in the experimental data. So noise is, as I told you before, okay, from the sources that I mentioned just now, but outliers is something that you don't expect. It suddenly come and it looks weird. For example, this one. This is considered outlier data, and if we get this kind of outlier, we have to delete, okay, because it really will disturb our best fit accuracy, which is above 90%. So here they show the red data, the red point as a black box data, and the blue line is the estimated of the model. And of course, this one is the input. Okay. So we go to the examples here. Okay, find the transfer function of the unknown system. So data is given and plotted. Okay, as shown here. Okay, so you can see that this data, by looking at it, is a first order system. Okay, first order. So what important for you guys is to identify the final value first. Final value is equal to 2. And then since first order system, we have to use the second strategies is to find the time delay. Okay, sorry, time constant, not time delay, time constant. So according to the theory, time constant is 63% from the output, the final value. Okay. So what is 63% multiplied by 2? Nevin? 63% multiplied by 2 volt. Hello, Nevin.
1.26. Sorry, 1.26.
1.26, approximate,
Yeah,
1.26 volt is something here, let's say here. Okay. And then it goes down here. So this is the time constant. Okay. Time constant that under the concern, and is about 0.03 maybe. Okay. So what we do is this is the first order system. The input is unit step. So transfer function can be determined by measuring the time constant from the graph. Okay. So there is 63%, which is the 0.0244 seconds. So this is tau, the time constant. So the model structure for the first order system is here. Ts is equal to K divided by S plus A, where K is the gain, A is the pulse value, and A is equal to 1 over time constant, which is 1 over 0.0244. Okay. So the A value will be 40.98 or roughly 41. Okay, so final value can be calculated like this. Okay, final value is equal to 2. So you equate to 2 equal to K divided by A, because we want to know the value of the gain. Okay, so K is equal to 81.967. Okay, 41. Okay, this one is 82 lah, lebih kurang, Right, so the transfer function is GS is equal to 82 divided by S plus 41. Okay, to make life easy, okay, we use an integer number. Then we plot. Okay, then we plot using a MATLAB. So I hope you know by now how to plot this. You know how to plot this using MATLAB, guys?
Yes, Prof.
No, Just to show you, share a little bit. Maybe some of you didn't know how to do it. Okay, so I share my screen. Functions. G is equal to 82. Okay, 82 rough value divided by S plus 41. Okay, and then a step go to G, and then put a grid there. Right, so I share the figure. Okay, can you see, guys?
Yes, Prof.
Okay. So you use a right click, and then you can find the characteristic, which is the rise time, settling time, transient time, and steady state. Okay, so it didn't give a tau. Okay, so just find the steady state, okay, which is equal to 2. But for time constant, this MATLAB software unable to give in the menu, so we have to somehow find 1.26 output by scanning. Okay, 1.26, 1.2, 1.26. Okay, somewhere there. Okay, so that is the time constant. Okay, and which is equal with the data that given. Okay, in the slides. Okay, so I share with you the figure. Okay. Right. So we move to the next one. Okay. So this is the final transfer function. Then we simulate using MATLAB. Okay. Then we verify. Okay. It's supposed to be two graph in one. Okay. It's supposed to be, if you want to compare two graph in one plot. So it's good kalau kita boleh tunjukkan lah. Right. So it should be follow like this. Then from there we can calculate the best fit. Okay. Of the data, the output fit to the input. Okay, we go to the example 2. Same question as well. Okay, find the transfer function of the unknown system model. So data is given. Okay, then plotted. So by looking at this, okay, we know that this is a second order category under them. Okay. So under them, so finally we find the final value first. So final value is about maybe 11, okay, approximate. And then find the settling time or peak time. Okay, so if you want to find the settling time is plus minus 2% of the final value. Okay, so in this case 11, so it can be 10.98 or 11.02. Okay, volt. Which one comes first? So if this one comes first, that is the TS. If this one comes first, this is the TS. Okay, is the tolerance of plus minus 2%. So after that, we measure it. So it's about 2.62 seconds. Okay, it's about 2.62 seconds. Is somewhere here. Okay, the settling time. Okay, if you do the amendments of the graph, so the maximum value, which is here, 13.82. Okay, and the final value is 11.03. Okay, so 13.82 volt is the maximum, the peak value. 11.03 is the final value, and the settling time is 2.62 seconds. So we try to find the overshoot first. Okay, which is 25.3%. Okay, so this overshoot need to be because why we calculate overshoot, because we want to find the value of the zeta and omega n, right? So how we get here 0.4 is either you use the formula, okay, number one formula, or you derive. Okay, you derive like this. Can you see my whiteboard? Can
Yes, Prof.
Yes, Prof.
25.3%. So exponent 1 over zeta square 25.3. So exponent (0.253). Okay, and then we apply ln. Okay, we apply ln. Can you help me? What is the ln? for 0.253. Nevin, can you help me? Ln 0.253.
Negative 1.374.
Okay, so negative can be cancelled. Okay, and then you simplify. So zeta is about 0.4. Okay, you simplify this one. Okay, simplify this. Carry on. Okay, then you will get the value is 0.4. But our settling time is equal to 2.62. But this one is equal to 4 divided by zeta omega n. Okay, so 2.62. So we already know zeta, so omega n now become
3.82.
berapa Fang? 3.82
3.82.
radian per second. Okay. So this zeta and omega n, the damping ratio and undamped natural frequency, is important because excuse me, because you want to fit into the second order model structure. Okay. Which one? This is the gain, this is the damping ratio, and this is the omega n. And to find the gain is we simply equate the final value 11.03 divided by k over omega n square. So k is equal to 11.03 multiplied by 3.82. Okay, so you will get 160 or 161. Okay, so this one is 161. Okay, so this one is 3.1. Okay, and this one is considered as 14.6. 14.6. Okay. So and then we observe the plot. Okay, plot it because it's a second order. So just start as usual the program. Okay, so you already declare S, so straight away G is equal to 161 divided by S square, okay, plus 3.1 S multiplied by S plus 14.6. Okay, so that one, and then step G, then the grid. Okay, so you can see the plot now. Can you see the plot? Okay, there's a plot. So use your mouse, right click. You can see the characteristic, the peak response, the rise time, settling time, and the steady state. Okay, which is 11. Your settling time is 2.2, and your peak time is 0.891. Okay, so more or less equal to the one that in the slides. Okay. Okay, so okay, guys, so this is it. Okay, as shown in the slides, and then some simulations, and validations is almost equivalent. Okay, between the real data and the model. We call it as a real data. This one is estimated model. Okay, we just estimated and it matched. It's supposed to be one graph, you know, and follow the value there. Okay, it should be follow as the data and the model must be agreed with the percentage of above 90%. And example 3 here is quite similar, but the peak time is given as 4 seconds, which is here. Okay, 4 seconds peak time. And this one, the maximum value is 1.4. And this one, the final value is about 1.0. Okay, so from the graph, you use the formula for overshoot. 1.4 minus 1 or divided by 1 multiplied, so it's 40%. So 0.28 is come from this formula or using the equation that I just showed you before, okay, which is the exponent minus pi zeta 1 minus zeta square equal to 0.4. Okay, so you put natural logarithm on the left and on the right, so you will get the zeta value is about 0.28. Okay, so peak time from the graph is 4 seconds. So the peak time formula is different from the settling time, which is pi divided by omega d. And omega d is equal to omega n square root 1 minus zeta square. And then from here, you already know the zeta. So just find omega n. Okay, so omega n is equal to pi divided by 4, 1 minus 0.28 square. Simplified omega n, so you will get omega n is equal to 0.82 radian per second. Okay, 0.82 radian per second. Okay, and as usual to find k, so k is divided by omega n is equal to 1. So k is about sorry.
Yes.
You got answer outside?
Yes.
You went without?
Nevin, off your mic. Nevin. Thank you. Right. So hence k is equal to 0.669. So substitute the value in the model structure. Okay, of second order. So you get 0.669, okay, divided by s square, 0.458 seconds. Then you plot, you do the code as I showed you before, and then you simulate. Then you get the validation, which is equivalent. Okay, by looking at this, okay lah. Okay, so it's equivalent. Agreed. Okay, any question before I proceed? Any question? Okay.
No, Prof.
Okay, so we continue to example 4. So the unit step response of a linear control system is shown in the figure below. Find the transfer function of the second order prototype to the model of the system. Okay, same. Okay, about the same. So the TS is 0.0245. So this one is equal to 4 divided by zeta omega n. Okay, and then the final value is equal to 1. Peak value is 1.25 with the peak time 0.01. Okay, 0.01 second. Okay, so make life easy. Right, and then you just follow as example 3. Okay, so the solution is shown here. Zeta value is 0.404, and then omega n is 3.343.4 radian per second. Then the K omega and the K value is 117.16, where this one is come from equal to 1.0. Okay, so 343.4 square multiplied, so you get this, right? So this is our target. Okay, this is from the assignment and previous student project assignment, where they are given measured data here, and then they have to find the transfer function. So be careful, since our this one, okay, is start from 0, so the time delay is equal to 0. Okay, but in this case, the time delay exists. Okay, so the time delay, see, if you calculate the box there, 1, 2, 3, 4, 5, so it's about 0.5. Okay, 0.5 seconds. So there is a time delay, and usually the time delay is represented by minus 0.5s. Okay, in the continuous form. So the estimated model shown here. Okay, this is how the student estimate. So they estimate, then they superimpose the graph. Okay, it looks that the green line. Okay, the green line is the data, real data, and the blue line is the estimated model. This is what I expect from the assignments later. Okay, so this is the model that they got. Okay, so exponent 0.49 actually is a 0.5. Okay, s squared 3.631 plus s plus 21.17. Example 6 also, where we have another case, but this one the time delay is 1, 2, 3, 4, 5, 0.2, 0.4, 6, 8, 0.25. Okay, 0.25 seconds. Okay, and student estimate this one. This one was given by me. Okay, and this one is the student come out with the proposed estimated model, and it looks better. Okay, this one is very good. Okay, full mark. Okay, very good. So you can see that the real model has been fitted by the estimated model. Okay, example 7. Also, the time delay is about 0.8 seconds. Okay, and the student try to estimate the real data second order, and also this one is very good as well. Okay, compared to the first one, the second one is also good. Okay, so more example is from the this website. Okay, you just click the link given. Okay, and I give some compliment to all my students. Okay, program to generate data for a time response. Okay, so this is the way. Okay, first we define SS and then we define the G, and in this case there is the exponent, meaning that there is a time delay which is equal to 0.1 second. Then generate the step response y of this step G, and then I'm not sure whether this one can be used or not. Okay, if you can tell me. If you don't know, never mind, and then don't forget to step G. Okay, and then you can copy paste the data from the workspace. Okay, the data will be from the workspace of MATLAB. Okay, last time the old MATLAB versions and the old Excel version can communicate each other. So that's why I wrote this program, write data to Excel. But currently, all a new version of MATLAB and new version of Excel, this program seems didn't work. But if you can make it work, you tell me. Okay? Okay, guys?
Okay,
Are you
Prof.
sleeping? Are you sleeping? It's 2:30, 2:36. Okay. Lagi 20 minit habis. So this is some exercise for you. I take it from the test, okay, to share so that you know what is test one will be. Okay. So overshoot is 39% and settling time 16 seconds is given. Okay. I think the final value is 1. Okay. And then this one is 1.4. Right. So this one as well. So I think this one is the first order. Okay. So you can do it by yourself. This one is second order. And this one is exercise 3. Okay. I think this one is most probably either second order, undamped, or first order. Okay, but you can try. It's either first or second order. Okay, second order we have 5 category. Okay, first is the underdamped. The example shown is underdamped, where zeta is between 0 and 1. Then undamped, where zeta is equal to 0. And critical damped, where zeta is equal to 1. Then overdamped, where zeta is greater than 1. And number 5 is negative damped, where zeta is less than 0. Negative is unstable. Okay, unstable. There is exercise 4 as well, so very long explanations. But at the end of the day, is the graph is matters. Okay, you can see that here is given as amplitude 1.5 with the times. This one as well. So what is the question actually? Assume the is obtained from the using the assume a second order model by unit step input. Find the corresponding transfer function. Okay, so I think this one is quite easy. So 1.4, 1.6. So in between is 1.5 most probably. Okay, then you use this one as peak time. Okay, get the peak time, get the settling time, or either TP or TS, and final value is equal to 1. Okay, so you can get the mathematical transfer functions. So that is for the time response, and then for the frequency response identification is the second one, which is the simplest way to experimentally characterize the frequency response of a plant by injecting a sine wave, okay, to the unknown system, and then capture the data and save it in the workspace. Okay, you can use real-time workshop MATLAB to do this black box experimental frequency analysis. Okay, so let's say we have a 12 sine wave, okay, increasing frequency from 0.2 to 6 radian per second. We capture the output and then we plot. Okay, you can see that what happened. at the low frequency. Okay, this is at low frequency and this is at high frequency. You can see that at high frequency, the magnitude of the input and output change. Okay, magnitude change. Okay, between input and output. That is the first observation. Second observation is the phase lag different. Okay, there is a phase lag between the input and output of the signals. So experimentally, we determine this. Okay, is the black box data derived from the laboratory. So you can see that the input is here, the first frequency, and then the final frequency. So you can see the amplitude ratio, which is V out over V in. Okay, is ratio. Okay, so start to decrease from 1.19 to 0.1, and then the phase lag give a negative value. Okay, why this negative value? Okay, is because input lead output. Okay, so that's why you get a negative phase lag. But if the output leading the input, meaning that all the phase lag will be positive. Okay, so phase lag have negative and positive. So phase lag is negative when input is leading the output, but phase lag is positive if output is leading the input. So disadvantage using a frequency response is one is very slow, okay, not efficient or not practical. But when attempting a frequency response characterizations of a steam or water heat exchanger, noted that it was difficult to produce a good quality sine wave input to the plant when using the control valve. Okay, so since the range of the frequency span from 3 over 3.5 orders of magnitude, which roughly is about 0.001 radian per second to 3 radian per second, the testing time was extensive, is very long. Okay, but it can be done. Okay, but quite long. Okay, so additional problem of sine wave testing that are the gain and the phase lag is very sensitive to bias, drift, and output saturations. Okay, due to the equipment or due to the measurements. So in order, it's often difficult in practice to measure accurately phase lag and give further potential problems and effects of the non-linearities. But anyway, still being used, okay, as the pre-testing of the unknown system, and the tools used is boot plot. Okay, so I believe that you already learned boot plot. Okay, so is the log magnitude versus log frequency and the phase in degree versus log frequency. So this is a sample of a first order system, okay, which is given by these equations. So when you apply Fourier, the impulse and step response, it will give you something like this. This is for the impulse. This is for the step. Okay, there's time delay there. And this is the boot plot, which is the gain and the phase versus log frequency. So we can estimate the frequency response, okay, by looking at the magnitude and the phase difference. Okay, so these two important is very important, which is the magnitude of the V0 and V in. Then we find the ratio V0 over V in, and then the phase lag. Okay, and we have to make sure that so in this case you can see that the yellow is the output, the purple is the input. So you can see that the input is leading the output. The purple is leading the yellow line. So the phase lag is negative. Some review of the boot plot, okay, before we start the problems, okay, for you to read. So I will skip this one, okay, just to review the shape of it. Okay, so this one is a sample of zeros, okay, when the transfer function have zeros only, S, okay. So the slope is positive, okay, positive slope. And for S square, okay, and for this one is the 1 over S, okay. So the slope is minus 20 decibel, this one, per decade. But if you are 1 over S square, so it become a minus 40 decibel per decade. Okay, previously, this one is positive 20 dB per decade, and this one is positive 40 dB per decade. Okay. Okay, so this one is one of the example of poles at minus 0.5. Okay. You can see that the corner frequency is 0.5. Okay, it goes here and it goes up like that. Okay, and the phase is goes here like that. Okay, so the corner frequency is 0.5, is the same value as the poles. Okay, so this one, the slope is positive 20 dB per decade. But if you have a poles at the poles value, okay, let's say this one, okay, the poles value is 0.2 minus 0.2. You can see that the corner frequency will be 0.2. Okay, so it goes like this and it goes down. Okay, so that is the magnitude where the corner frequency occurred at 0.2. And if you have something like this, two poles value, the first one is 1 divided by 0.5 is equal to 2 radian per second corner frequency, and this one is 1 radian per second corner frequency. So 1 is here and 2 is here. Okay, corner frequency. So when we add together, it becomes the total. Okay, this one is the total of the gain and total of the phase. And this one as well. Okay, so is minus 0.1 poles value. So in fact, is twin. We have double poles at minus 0.1. Okay, so the corner frequency at 0.1. So just add it add each other. So minus 20 dB plus minus 20 dB per decade. So it will be minus 40 dB per decade, the total. Okay, and this one is for the second order complex conjugate pole. Okay, and here is if you calculate the corner frequency is about 1. Okay, over here, corner frequency, and this one is minus 40 dB per decade for the gain slope, and the zeta value is 0.707. And this one is quite unique because it's only complex poles at complex value, which is plus minus J2. Okay, so the plotting of the gain is there is a peak over here. Okay, at 2. Okay, because the system is undamped with zeta is equal to 0. And this one as well. So for you to explore 4 poles value and add together, and the transfer function with time delay minus 2s, which is time delay is equal to 2 seconds. Can be plotted of the board diagram. How you want to know whether the system have a time delay or not? Just look at the phase. Okay, so this is the phase. can see that the total phase plot, this one. Okay, it goes down there and then it goes down. Okay, so it's not going to minus 180 degrees. Okay, it goes down. So meaning that the time delay exists. Okay, for the system. All right, yes, we stop here because I have a meeting and briefing at 3 o'clock. Okay, is there any questions you want to ask? Any question, guys?
No, not bad.
Prof.
All right. Okay. So I see you back again on Thursday, 11 o'clock. Okay. Thank you very much.
Prof. I have a question.
Yeah, please.
For the data, can I save to Notepad?
Data.
Yes, from the previous question, the exercise. Can I save to Notepad instead of Excel?
Can. Because why we use Excel? Because we want to plot the graph. But in Notepad, I'm not sure whether you can draw a graph. Can you draw a graph
Yes.
from the?
Because MATLAB have the code for the graph.
Okay, that's good. Okay, you can apply in the assignments, which will be released very soon before semester break. I think it's a good idea. Okay.
Okay, thanks, Prof.
Okay, thank you very much, guys. Okay, I see you on Thursday. Bye.
Thank you, Prof.
Thank you, Prof.